First of all, our next talk is sponsored and reserved by our silver partner for this year, Wargaming. So we would like to thank them, and we hope we are going to have many more partnerships, since they were our partners for the last 3 years. Our next talk is going to be titled Enhancing Personalization Using Recommendation Systems and Multi-Armed Bandits. Our speaker will be Dmitriy Matveev, the head of data science and strategy at Wargaming. Today he will show us their mechanics behind recommendation systems, which have driven a remarkable 40% revenue uplift in their company. Can we have a warm welcome for Dmitry?
Okay, thank you guys. I'm glad to be here, and very interesting how to change slides. Maybe I can have some kind of tool for this technology. Yeah, and it's really funny that I'm the third speaker with the black slides. Very interesting. Okay. So at Wargaming we have plenty of games. It's a war games actually, and the flagship is World of Tanks, of course, and World of Warships. If you haven't played this yet, I definitely recommend. It's a good game, at least try it, please. And also we have some mobile games that we use for testing machine learning prototypes, and that then scale it to the big games like World of Tanks and so on. And one of these games is Bowling Road. It's top one game on mobile, and we just use it for testing different things. I work as head of data in a mobile department where we have a lot of different games, and we handle different tasks, right? Because Wargaming is a complex and a huge organization with different departments, and every department have its own scope of things. And we cover data analytics, some A/B testing, and pricing, dynamic pricing, and also we have some exciting projects like recommendation systems. Well, recommendation in game, I don't think it's a very common task, but it might be the most obvious. Of course, game designers strive to make events and offers for players to engage them more, to activate not very active players and make them from players to pairs, right? So for our task was to create this system that help us to make a personalization. We have some offers, we have some starter packs, and so on. And we have a really tight schedule for development, and thanks God, we doesn't have any requirements for latency for some part of this system. And we have hot users, and it's very good. So we can put this task in some practice-term bed and said, okay, we need to recommend something, so we can make just some ranking model, learning to rank, or maybe we can just predict if a user will purchase some item or not. And using this, recommend something to them, but we want to stick to some more common implementations, like content-based systems, where we take some content of the item. For example, if I like the movie with Cillian Murphy, I guess it's might be good suggestion to me to recommend another one film with the same actor starring it. And another one is collaborative filtering, collaborative systems, where we don't bother about some features. We just have history of ratings, how user E rate the item G, and so on, and try to reveal the hidden factors and use them to restore rating for the users that doesn't have any collaboration with other items. And also we have a more complicated system. It's a hybrid that combine these two approaches. And most companies use this one. And the first thing when we received this task was searching Arxiv and Google Scholar to find the best possible solution for this problem. And we start thinking, okay, we have to implement some deep learning models. We need some advanced techniques. Let's use this, that. We have a nice example from Meta, from Google. We have Merlin from NVIDIA and so on. Let's implement Bloom filters, learning to hash function, and so on. But wait, we have only one problem. We just want to restore ratings for users. And for this, even some SVD algorithm, well, with extra steps, and its basic example, will be enough, right? So when we start to think about implementation, we have three types. It's offline, it's batch system, and real-time system. Most of the such solution from big tech companies or just tech companies combine these two approaches, like offline and real-time, and we will see it in the next slide. But for our task, when we have very strict deadlines, we work with versions, and we have warm users. We won't be very quick, and we want to have some cost-efficient solution, right? So we stick in this problem to offline system because we want to try more complicated algorithms in the future, and the same deep learning here, and that's what we actually done, but we skip this part here. So you can see from the tech companies we have offline and online parts like an Alibaba, Dardosh, and so on, and even some of these companies write the query languages to improve speed and latency for receiving recommendations. But, well, to implement such a complex system, we need to have one. But we lack of foundational recommendations, so we just have to build something from start with. And typical workflow for recommendation consists of this part, like every recommendation. We want to filter our items, get best candidates, so we retrieve information and filter it according to our business logic, because we can have a lot of limitations here. Then we need to extract some features to input it to some models. We want to score items to find the best possible items for the users, and also rank it. If we have multiple scores, multiple models, we have to rank it one more time to get best scores. And it's infinite loop where we train model, collect data, get features, and so on. So yeah, but let's example that we have billions of items, billions of candidates, and of course we want build something complicated, but most companies and most systems consist from two parts. The first part is some lightweight model with trying to optimize recall here. When we shrink our data set from billions to maybe hundreds or thousands, and then we use a second step model. It's more complex one and more resource intensive, and try to make try to make ranking and find most relevant items, and here we try to maximize our precision. Well, and in the end we have about a dozen of items to suggest for user. But let's start with the data, right? So we have multiple sources of data. When we're talking about games, we have huge amount of logs. Like, I think it's too much. And feedback from the player can be explicit and explicit. We have some item usage, some likes, ratings. We also have clicks, purchases, item views. Player can just look at item, look at something, try to scroll it, and so on. And we don't know if this scrolling is implicit intention or what is it? For example, we have a lot of loot boxes in games, right? So, and a lot of items, and these items can be upgraded by receiving resources from loot boxes, but it's random. And let's imagine we have about 1,000 of items, and probability of receiving the most wanted item for user is really low. And when users just receive these resources, upgrade items, if this upgraded was because he really loved this item, or is it because just to be aligned with our progression system, because the more you upgrade, the higher overall level player have, and so on. So we took everything we have, and the whole process of data selection was about 26 hours. Well, we just killed the process because, I don't know, maybe it will take a week. And we just rewrite the whole data collection process to incremental approach where we use in delta method. And with this, we speed up the computation time up to 100 times. Well, it's very cool. And here we skip this part where we try to take different features, try to use some computer vision to select more features, more embeddings from the images, and yeah, it's really long. And let's stick to the logic, because I think every game has very complicated logic. It's very complex, and so we have lots of, in this game particularly, business rules. So, for example, level restrictions. It's pretty obvious that player with level 8 cannot access the items with level 20. Well, pretty obvious. And we can show items and sell items from events because we have separate offers for these. Separate layouts where player can get these items. Also can sell collaborative items because of legal. We can sell premium unique items because, well, lots of different stuff. And it seems like after all these filtering, according to this logic, low-level players have nothing to recommend. And this system focusing on the high-tier players, because they have about 200 or 100 items we can just rank and show. So let's look at the system design we have here. So we have some hot features and some cold features. For this module, we're not using our hot features so from message broker, and we just use cold features, pre-process them a little bit, and put in the storage. Okay, data from here we use it then for monitoring quality, data reach, and so on. And this part with recommendation, we have inference, we put it in AWS, and then wait for the player to come to the game and then communicate with them. So it's not real time, it's an offline system, but we do it really frequently, like a couple of days, every day. So sometimes we don't want to recommend from the full set of items. We have millions of items, but we know that there is 10 best item and want to select the best one. And here we don't need some recommendation system. We can just stick to the multi-armed bandits, and it's very convenient and popular approach. Yeah, so the first impression is very important, right? Like in every product, in every game, especially in a game. And we have starter packs. Which one of these 3 starter packs is the best? Well, I don't know. But we have to know to suggest something for player to make it pair. And we see the correlation between the how fast player convert to the pair and LTV, right? It's again pretty obvious. And we have very strict requirements for latency, about 30, maybe 60 seconds, or it can be a little bit more. It depends on how fast the player completes the tutor. And we wait for some features to collect from the new user, from our data providers, to understand from which media source player come to us and so on. So it's really a little gap. And we want to increase conversion rate. So multi-arm bandits or contextual bandit, name it, we have very wide use. We have a lot of use cases just because it's very adaptive algorithm. It can relearn in real time. It's a good balance between exploration and exploitation. And it's pretty easy to implement. Let's look at the list of possible spaces where we can use it. It can be content recommendation system like YouTube, where you log in and see best videos that suits you best, or ad optimization like Google Ads or Facebook Ads, some e-com like Amazon, Ananas, I don't know. And we also can use it in game design and some personalized experience for selecting offers and layouts. And let's look at some cases from the Netflix where you just log in and see different thumbnails, different covers, like art covers for films and series, where the Netflix also adopt the contextual bandits for this task, or their doors. They use some geolocation levels, like country, region, market, districts, and so on, to understand how what to show to the new users in new locations, and then algorithm optimize to the best possible suggestion for the user. You can just right now log in the Vault, and you will definitely see some recommendation from Serbian cuisine, right? And if you're in London, you definitely will see some fish and chips. This will be the first recommendation. So what if we take the same logic and use features that we can extract really fast? It's a country, definitely. It's platform, media source, and some data about date of registration. Maybe day of week, maybe it's months, because some people install game in Monday and some people in Sunday, and completely different people sometimes. Yeah, and on the left you can see the how algorithm explore and adopt to the different starter packs. We have 3 actions here, 3 arms, and 3 offers actually, and it is simulation where we can understand how well and how fast this algorithm will converge. So moving to the system design, we try to be very eco-friendly, actually cheap, cost efficient. And here we already use our hot features from Kinesis, where we put these 4 features like country, platform, and so on to the online part. We have offline part for this algorithm where we retrain our weights. We have online part where we do similar things, and then recommend really fast recommend the offer for the new player. Yeah, and for all of this we use some basic things like flows, Snowflake, so on, just to, and some data visualization tools. Yeah, but after all these exercises, after two systems, we understand that it's very complex to have in one process collect user information, collect embedding of the user every time, and we think that it's best solution just to separate this process, like guys from Meta dropped the paper in this year, where they have some upstream model with user embeddings and then downstream into the other models, other services. And it's really good if you have lots of recommendation system, lots of different offers and so on. It suits us really well. So let's look at the results. And after all this system was implemented, we have uplift in revenue of 45% among high-level players. So of course, overall on the whole set of users, it's lower, but we focused on the high level, as I mentioned previously. And we have uplift in repeated purchases about 20%. From the starter pack, we have uplift over 15%. All of this results from A/B tests that we have conducted. And currently, we changing this architecture. It's actually fourth iteration of changing it. And sometimes to implement something that can generate money, you don't have to spend lots of resources. I think it can be done in 2 weeks, something in 3 weeks, so it's like one sprint, right? And we can deliver some solution that can generate money right now, and then we just make it better, 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 better in just infinite process. And sometimes we can just start from the little and with lower steps go to the something big and beautiful. Okay, so thank you very much.
Does anybody have any questions for Dmitry?
Hey there, Boyan is here. Thank you, Dmitry, for the presentation. Quick question for you regarding mid-tier users who are not currently using your application. Did you work and did you have any AI solution for getting them back and putting them in a spot to become higher tier so they can be better revenue providers to you? Thanks.
Yeah, we have different solutions. Some of them are based on the segmentations that I guess you've seen previously on one of my first slides. Just a fancy picture that is not usable at all. But well, we can group it and select users according to their purchase ability or engagement, and make different clusters. And we have experiments where we take some cluster like sleeping whales or minnows. How can we make the average check to be a little bit higher, and every time a little bit higher? And we make segmented offers. So the same offer, you can see it here, for example, the same offer, and every person sees it same offer, but the users that can pay a lot see lower prices and lower content in it. So they can buy it, but it's not like a huge amount of different resources. And it's worked really well with low-tier players, like minnows. And it also depends on the offer. So you have to select wisely and of course conduct A/B tests.
Thank you.
Hey, my question is how easy or difficult is then to you mentioned that you test models in this game and then you need to somehow do it in the other game, which is completely different. So is that a challenge, and do you always do it, or how is it?
Yeah, the most complex thing here is to work with data, because data sources can be different, or data structure, data model can be different in other games. So the first thing, we have to incorporate the data, and if we have some sophisticated pipeline, we can just change it a little bit, fine-tune, and it will be it. We can use it.
Actions are always the same, like.
It depends.
Or,
No, it depends.
Anybody else? Here we go.
The graph with the multi-armed bandit, one of the options very quickly drop down and stay consistently down. Why not eliminate the worst performing arm if it's shown to be really bad?
Well, we have here not one model. It's contextual, so we have like lots of models for different cohorts or clusters of users. And for some of them, the previous slide was just from the simulation, right? So it's on the whole set of users. But on some subset, the blue offer can be better than yellow. So it's depends.
Thank you.
Any more questions? Okay, then we're done. Thank you, Dmitry. Can we have a round of applause?